Gauge Theory Virtual. We are pleased to have Zhenkun Li talk about Instanton Floer homology of 1-1 knots. I'm going to mute and turn off my video and let him take it away.
All right. Yeah, thank you. Let me share my screen. So, yeah, great. So today, thanks for the introduction and thanks for the invitation. So today I'm going to talk about the Instanton Floer homology and 1-1 knot. And everything is a joint work with EFN. Okay, so right, so let me start with a more general setup. So let's see, first for closed three manifold, oriented three manifold. So let's see why is a closed oriented three manifold. Oh, then there is a combinatorial way to describe this three manifold, namely the Higard diagrams. Fine. So right. So this consists of like an oriented and genus G surface with two set of arcs, which we usually write alpha curves and beta curves. Right. So and well, a three manifold can give us many Higard diagrams, and the Higard diagrams also determines the three manifold. Right. So so for the construction, well, let me say a little bit more. So from sigma alpha beta to y. So basically what we do is we attach three-dimensional tool handles to a secant copy of sigma and along the curves, the alpha and beta curves. Well, let's see, -1 cross alpha 1 up to -1 cross alpha g, and then 1 cross beta 1 up to 1 cross beta g. And of course, we then capping off the spherical boundary. And then we get a closed three manifold, which is our three manifold y. Then, well, of course, well, if we have a three manifold, we can also go back and have this Higard diagram. And well, there is a similar construction for knots. Well, for the pair y and k, where k is a knot inside y. So basically, we just not attaching the last beta curve, and then capping out the spherical boundary coming from alpha handles. Then we get a three manifold with a toroidal boundary, which is the knot complement yk, and beta g is the meridian of k. Okay, so from this data, or from this combinatorial data, we can actually construct the Higard Floer homology. So due to Oswald and Stubble. Well, of course, they constructed 4 different flavors of Higard Floer theory, but I just only looking at the hat version. Well, roughly speaking, this is the Lagrangian intersection Floer homology. Well, let's see. Homology of we have 2 Lagrangians. One is T alpha coming from alpha curves, and the other is T beta coming from the beta curves. Well, inside the symmetric product of sigma. Of course, well, we will need some auxiliary data to specify the spin-sys structure. To specify the symplectic structure and looking at this Lagrangian intersection Floer homology, and everything is well defined, and this becomes a topological invariance of our three manifold. And a very good thing for the Higa-Floer theory, or at least for the hat version, is that, well, it is computable. So there's an algorithm introduced by Shaker and Wang, which says that, well, giving any Higa diagram of y and yk. Yeah, so I'm sorry. So maybe let me see one more things before writing this. So of course we can have a Higa-Floer homology for a single three manifold coming from its Higa diagram, of course, and we can also have a Higa-Floer homology for the pair y and then k inside it. So coming from similar constructions. So okay, or then there's an algorithm to compute the Higa-Floer homology for y, or this pair y and k, from the Higa diagram. Of course, well, if we're given of course, they did this computation on nice Higa diagrams, and for a general Higa diagram, we need to first, it's a sequence of moves to make it nice. But it's doable. All right, so but the Higa, on the other hand, so there are many other Floer series. Many other Floer series. Well, it just begins from Floer, and he introduced the Instanton Floer theory. And then, well, slightly later than Oswald and Stubble, there's the construction of monopole Floer theory by Kronheimer and Morfka. All right, and then, well, more recently, there's the ECH constructed by Hutchings. They are related theories, and well, but they have all very distinct natures. For example, for Higa-Floer theory, yeah, it's related to the Higa diagrams, and it's the most computable. And for instance theory, we can study so it's more related to the representations of the fundamental groups of the three manifold. And for monopole theory, is also related to some geometric structures. And for ECH, of course, is closely related to contact geometry. So they all have different natures. But for all the rest, well, I guess, well, they're constructed through, well, let's see, at least for this two, well, they are constructed through a set of partial differential equations on the three manifold y, and also the infinite cylinders r cross y. So let's see. So the monopole, or Instanton and monopole theory are constructed through, well, PDEs on y, or r cross y. So, well, it's difficult to compute. Well, from the definition, we cannot say solve the differential equations and write down every generators and compute every differentials, and then write down the Floer homology. So this will be a big question about how to compute it. But so for monopole theory, and also for the ECH theory, this has been done because we can identify them with the Higa-Floer theory. So the remarkable theorem by Katluhin, Li and Tops, and also by calling Gigini and Honda, and plus also Tops' work. So we know that the Higa Floer, the monopole Floer homology, this is a suitable version of monopole Floer homology is isomorphic to the hat version of the Higa Floer homology. Right. So and well, it's also holds for ECH. So and also well, if we look at the version for knots, then plus Johash's work and also well, likely for Baldwin Savick. So we know that a suitable version of the knot Floer theory, HFK hat of Y and K, occurs on HM, tilde, and KHM monopole Floer homologies. Of Y, or it's YK of this pair Y and K. So if we only need to compute the Floer homology, then we can just look at this identification and then compute the Higa Floer theory, and then automatically scout what it is for monopoles. But it's not known for instanton theory. How about the instanton theory? Well, as I just said at the beginning, so the Higa diagrams well determines the three manifold, right? So if we write down a particular Higa diagram, then the three manifold is determined. And the instanton theory is a topological invariance of the three manifolds. So there is an implicit relation between the Higa diagrams and the instanton theory. So, but can we just read some of the information? So can we read some information about the instanton theory from Higa diagrams? Right, so this is kind of the main question I'm going to talk about today. So and right, so but before we really go into present our main theorem, but let me say more about the instanton theory. So so it's back to Floer. If we have say if Y is a closed oriented three manifold, and omega inside Y is a one cycle, so that there exists a surface, well, of course, on closed oriented surface with an odd intersection with omega. Then, well, this pair is called admissible. Then there is a well-defined finite dimensional complex vector space. Which we write I omega of Y associated to the pair Y and omega. Of course, this is defined to be the instanton theory of the pair. Right, but then what happens if we have a three manifold with boundary? For three manifold with boundary, so we cannot do it directly if our three manifold has boundary, just due to some analytical difficulties. But we can have some extra data on the boundary, to help us, well, sort of construct a closed three manifold out of that three manifold with boundary and some data on the boundary. So this is called the balanced Suture manifold. And then Kronheimer and Morfka construct some make this construction. So let me explain this story a little bit more. So the definition back to Gabay and Newhash is that a balanced Suture manifold is a pair, well, where we have an oriented compact manifold, three manifold with non-trivial boundary, and gamma is closed oriented curves. And that divides, the boundary into two parts of equal Euler characteristic. Of course, well, here, well, I didn't explain the full conditions for being a balanced Suture manifold, but this is the key feature of it. There are a few examples. Well, let's see. Let's make some examples. The first thing, let's see if Y is closed and oriented, of course. Then we can form a three manifold with boundary by digging out a three ball. And we also want the suture. Well, let's take delta is a connected simple closed curve. On Y1, on the boundary of Y1, which is a two sphere. So we know that the boundary of Y1 is separated by delta into two parts. These are two disks. And of course, these two disks have the same molar characteristic. So this is a balanced Suture manifold. And the second, if we have a knot inside Y, and of course, Y is still closed and oriented, then we can look at the knot complement being a three manifold with boundary. So this is a knot complement. And now we can take a suture, which I call gamma mu. So this is a collection of two meridians, and with opposite orientation. And then if we look at so the rest of the boundary, so this is the union of two annuli. And well, this two part, of course, has equal characteristics. So that's another balanced Suture manifold. Okay. So for balanced Suture manifold, we do have this Instanton Floer homology. This is a theorem due to Kronheimer and Morfka. For a balanced Suture manifold, let's see. Right there, let me write M and gamma. Then there is a well-defined. Well, I will explain this a little bit later. Finite dimensional complex vector space. Let me write it as SHI of M gamma for M and gamma. Of course, this is defined to be the sutured Instanton Floer homology. Of the pair M and gamma. Okay, so for this well-definedness, the original proof for Kronheimer and Morfka is only up to an isomorphism. So their precise statement is the isomorphism class of this Floer homology group is a topological invariance of the pair. And later, some work done by Baldwin and Selwick is to improve this isomorphism class to only up to a scalar of non-zero complex number. So right now we can see, well, what are the one-dimensional subspaces of this Floer homology group. But I think today I'm only looking at the dimensions, or just like the isomorphism class of this vector space with vector spaces. So I'm not going to say too much about this well-defined list. Okay. So right, and of course, well, so previously I just introduced two special balanced Suture manifold for a three manifold, or a three manifold with a nut inside. So then Kronheimer and Morofka used them to define the Instanton Floer homology for three manifold and for the pair y and k. So I sharp of y is defined to be the Suture Instanton Floer homology of this balanced Suture manifold coming from digging out a three ball. And the pair, well, sorry, so this is k chi, is defined to be the Instanton Floer homology of the knot complement with the meridional sutures. So those are the Instanton Floer homology for closed three manifold and for the pair y and k. Of course, there's a conjecture. See, I sharp of y is isomorphic to HF hat of y, or tensor with the correct coefficients, and KHI of y, okay, isomorphic to HFK of y and k, tensor with C. So those are widely open conjectures, and the only thing we know is that for all the computational results we have already got, these two things coincide, but we don't know anything from existing examples, beyond the existing examples. Okay, so today, well, the main theorem for today I'm going to introduce is that, well, as I said before, we can raise some information about the instanton theory from the Higard diagram. So this is a joint work of me and Ben. So for any, but currently there is there's a technical requirement that we should look at the rational homology spheres. I will explain later why we want this constraint for the moment. So giving any Higard diagrams, diagram of y, or the pair y and k, of course, while k inside y is a knot. There is an algorithm to compute. Well, of course, we cannot currently we cannot compute the dimension precisely, but we can at least obtain an upper bound of say the dimension of the dimension, so dimension of I sharp of y, and dimension of KHI of the pair from the Higard diagram. Okay. Yeah. So, but of course, well, I just say if I just see an upper bound, then one can ask, well, if this upper bound is like 1,000,000, then that can't give us anything. So, but there are some examples where this bound is very good. So, as a corollary, we study what happens for one knot. So for any one knot, K inside a length space, I will explain what is a one-one knot later, but this is a large family of knots inside either S3 or some other length spaces. Right, we have the dimension khi of yk is at most the rank let's see, of the Heegaard-Floer homology of the pair. So recall above, we just say there's a conjecture that these two things should be isomorphic. So we can say this is like a conjecturally sharp bound for the dimension of incident Floer homology. And moreover, well, if K is inside S3, is also, of course, it should be a one-one knot and also a Heegaard-Floer L-space knot. Then this equality holds. So let me explain what is a Heegaard-Floer L-space knot. So K inside S3 is a Heegaard-Floer L-space knot. If, well, there exists, let's just say an integer number, so that the dimension of the, the rank of the HF hat of the n surgery of K is precisely n, right? So this is an equivalent definition of the Heegaard-Floer L-space of, let's see, the abstract value of n. So might have either negative or positive surgeries. Okay, so and also remark, all torus knot are both 1-1 and Heegaard-Floer L-space knot. Right. So this means, well, as a corollary, we can really compute the Instanton Floer homology for all torus knot. I think this is previously unknown. First of all, there are more knots which are both 1-1 and Heegaard-Floer L-space knots. So we also have many other examples. Okay, I guess I should pause for a while for questions. Just there. Okay, so if no questions, then maybe I will keep. Oh, let's see if there's a chat. Oh yeah. Okay. So let me keep going on. All right. So let me explain some details about the proof. So how can we get an upper bound? So from the Heegaard diagrams, because this Heegaard diagrams and the incident series seem quite unrelated steps. So the key ingredient or a key technical proposition is the following. So let's go back to balanced Suture manifold. And this is, well, recall this is a three manifold with boundary and some oriented closed curves on the boundary that divides the boundary into two parts. So we have a Instanton Floer homology for that. And let's assume there is something more. So theta inside M is a properly embedded arc. So that, well, the boundary of theta is also separated by gamma. Right. So as I said, well, this gamma will separate the boundary of M into two parts, And this means, well, the boundary of theta being 2 point will lie in the two different components separated by gamma. Okay, so and then what we can do is we can define or construct a new three manifold. So we can dig out a tubular neighborhood of theta and then find a new suture mu, where mu is the meridian of gamma. I'm sorry, a meridian of theta. So let me draw a picture or show a picture here. This. Okay, so what I have, so this this black thing is our three manifold and our M is inside. So this part, so the upper part is part of the boundary, and the lower part is another part of the boundary. So they are separated by this red curve, which is gamma, right? And this blue dashed arc is our theta. This blue dashed arc is our theta. And what we do is we, sorry, so there should be theta. And what we do is we dig out a tubular neighborhood of this arc theta and then give a meridian on the boundary. So this will be part of the suture gamma theta. So, and this will give us a new three manifold with boundary and a new suture. So the proposition.
So just make sure that I understood. So Zhenkun, the boundary of theta has, so it had one end is on R plus and the other end is on R minus.
Yes,
not
right. So
just two different connected components. They have to be on R minus and R plus, right?
Right. So yeah, that's great. So yeah, because I didn't say that because I didn't introduce this R plus and R minus, but let me say it right now. So yeah, great, thanks. So as I said, well, the boundary of M is divided into two parts. So we call one part R plus of gamma and the other R minus of gamma. So what we want is the boundary of theta intersecting R plus of gamma to be non-empty, and the boundary of theta intersecting R minus of gamma to be also non-empty. So the upper part is R plus of gamma. The lower part is R minus of gamma. Yeah, thanks. It would be better to say this more explicitly. Okay, great. All right, yeah. So actually, this is called a vertical tangle. The theta is called a vertical tangle. Due to introduces by Zhang and Xie. Actually, they define Instanton Floer homology for tangles inside suture manifold. So the proposition we want is that actually there's a so if theta real is boundary it represents a zero homology class inside the first relative homology of M with rational coefficients, then there's a rank inequality, dimension inequality. Well, if we look at the three manifold before and after removing this tangle, right, then there is a dimension inequality. So this is this is Instanton Floer homology for our original balanced suture manifold, and M theta is obtained from M by digging out this tubular neighborhood of theta. Of course, adding a meridian of theta into the suture. This is it. Okay. Right. So I will come back to the proof if we still have time. But let me first say, well, how can we use this? Why it's important? So now let's go back to the Hegar-Floer setup. The Hegar diagrams. So let's say if sigma alpha beta, so it's a Hegar diagram. Of y. Right. So then, well, what we do, well, what we do is we attach alpha handles and beta handles to a thickening of sigma. So there is a handle body obtained by only attaching alpha handles. This is a handle body. It's obtained by attaching two handles to the thickening of sigma along alpha handles, so -1 cross alpha 1 up to -1 cross alpha g, and then capping off the spherical boundary. Of course, well, the boundary of H is just 1 cross sigma. And if we further attach the two handles, attaching two handles to H along 1 cross beta 1 and up to 1 cross beta G, then what we get is just a 3 manifold removing a 3 bond. So this is the 3 manifold we want for defining the Instanton Floer homology. So recall I sharp of Y, this is the Instanton Floer homology of the closed oriented 3 manifold. This is defined to be the Suture Instanton Floer homology of Y1 and delta. So of course, we need to find a suture, which is a connected simple closed curve on the spherical boundary. But we also need to find some tangles to obtain inequalities. So what are those tangles? So what is a 2 handle? Well, a 3-dimensional 2 handle. Well, it's like a secant disk attached along the thickening of the boundary of the disk. So this is -1 cross di attached along beta I. And we look at this co-core. So this co-core is the tangle we want to look at. So we first pick the tangle and then we pick the suture. So pick delta on the boundary of the 3 manifold Y1 to make theta, well, being the union of all theta i's, to be a vertical tangle in Y1 delta. So this means, well, the delta will separate the pair of boundary point for each tangle, for each component theta I. Okay, so then, so our proposition implies, well, because, well, right, so yeah, I should say, there's one more requirement. So if Y is a rational homologous sphere, then theta I will represent a 0 class in the rational homologous sphere, sorry, in the first relative homology with Q coefficients. Then, well, yeah, because this is the key requirement in our proposition here. So then our proposition just applies, and we can find the dimension of Y1 delta is at most, sorry, so let me write it. Delta is at most dimension. So if we sort of digging out all those tangles, Y1, well, we put theta here and there's theta. Okay, so what's that? So this side is just the Instanton Floer homology, the frame Instanton Floer homology of the closed ring manifold by definition. And this part is another Suture Floer homology. Okay, so but there is an observation about this y1 theta, this is we're digging out tubular neighborhood of theta, or the tubular neighborhood of the union of this theta i's. However, as I said, well, the theta I is the co-core of a two handle. So if we digging out a tubular neighborhood of the co-core of the two handle, then we're just removing this two handle. So this is precisely the handle body H, or it should be called the alpha handle body. Yeah. So this is the handle body we just introduced by attaching along alpha curves. Okay. So this is good. So on a handle body, well, so the last thing we can do, this is due to my previous collaboration with Victor Gauche, that giving a balanced suture manifold H and gamma theta, where H is a handle body, there's an algorithm to compute an upper bound, right? Because we only need an upper bound for the dimension of the suture Floer homology of this pair, right? So in general, well, if we only have this inequality but don't know what is y1 of theta, or then, well, we just found the dimension of one instanton theory, one instanton Floer homology by another, so it's not simplify the problem. But for the special case where we're looking at a handle body, we can at least find an upper bound. So yeah, I think I still have time to explain this part a little bit more. So how can we do that? Okay, so let me draw Genius to handle body. Right, for handle body, well, there is a Moradin disk we can look at. This is the disk D here. Well, this is the handle body H. This is a compressing disk for the handle body, which will compress this Genius two things to be a torus, a solid torus. And in general, well, the suture will intersect. This is gamma theta. Gamma theta will intersect the Moradin disk D. So if D intersects gamma to be 0, or equivalently, if they are disjoint, then we know directly that this the suture Floer homology is 0. H and gamma is 0. Well, this is by Kronheimer and Morfka from the adjunction inequality in instanton theory. It's not going to introduce to explain the details, but if they do not intersect, then the suture Floer homology is 0. Okay. If their intersection is 2, then, well, let me show another picture here, like this. So if the suture gamma theta intersect the disk twice, then what we can do is do a suture manifold decomposition. So this is a suture manifold decomposition. And this definition is introduced by Gabay. And the theorem proved by Kronheimer and Morfka was that in this special case, what we know is the suture instanton Floer homology of the original balanced suture manifold will give us will be the same as what of it for the three manifold after the decomposition. So yeah, the decomposition, roughly speaking, is that we cut the three manifold along this disk. We do the compression of the handle body, so reducing its genius by 1, and then we cut and reglue the sutures. So this will reduce the genius of the three manifold of the handle body by 1. Of course, well, the last case, well, if D intersects gamma at least 4 points, then what can happen? So let me draw this picture here. So here we still have our gamma theta and our D here. So yeah. So what we have is we can find an arc whose endpoints are on the suture and whose interior intersect the suture exactly 1 time. So this is called a bypass arc. This definition coming from Honda. And what we can do is we can alter the context, alter the dividing set locally. So let me draw it. So originally what we have is like this. And this is the boundary of D, this boundary of D, boundary of D. And this is our arc. Yeah. This is our arc zeta. So what we can do is we have 2 other local change of the dividing set. And there's a theorem by Baldwin and Sawick. Well, is that there is an exact triangle from M gamma to that of M gamma prime. Let me keep my notation. H theta, HI, H and gamma double prime, and then going back. Okay. So of course, well, we know then there is an upper bound of the dimension by summing up the 2 other stuff. But so for these 2 other sutures, gamma prime and gamma double prime, what we can do is we can isotope them to make less intersection with the meridian disk D. So, but gamma prime and gamma double prime have less intersection. With D. So this is kind of an inductive step. So we pick an arbitrary compressing disk of the handle body and then look at how many intersections it has with the suture. So if the intersection is 0, then we're down because its Instanton Floer homology is precisely 0. Well, if the intersection is 2, then we do a suture manifold decomposition, and this will give us an isomorphism on the Instanton theory. And so if we have more than 2 intersections, then we use this bypass exact triangle to reduce the intersection and still obtain an upper bound. And keep doing this, we can reduce the intersection down to 2 and then do the decomposition. Okay. All right. Yeah, so this will give us a theoretical algorithm to do the computation. And luckily, we did that for all the 1-1 knots. Yeah. We do it for all 1-1 knots, and that happens to be a good stuff. So precisely the rank of the Higgs Floer homology. So I think I still get like 10 minutes, right? So then I will explain a little bit what is the 1-1 knot, about 1-1 knot. So the reason why we are looking at them is that the 1-1 knot have very good Higard diagrams. So let's see. Excuse me for a moment. Okay. So 1-1 knots K inside Y, where Y is a length space. Let's see, a 1-1 knot. A family of knot. That admit a genus 2 Higard diagram that can be parametrized by a tuple by, let's see, PQRS for integers inside Z. All right, so let me draw this genus 2 Higard diagrams. So this is a genus 2 Higard diagram. This means, well, our surface sigma has a genus 2 and alpha curve are just two curves, alpha 1, alpha 2, and beta curve, just two curves, beta 1 and beta 2. So, right, so instead of drawing a genus 2 surface, what I draw is a rectangle with two punctures. So if we glue the boundaries of the rectangle, we get the torus, and if we glue these two punctures, we add the genus by 1, so we get a genus 2 surface. So that's the genus 2 surface sigma 2. And then, well, we have 4 curves, and well, so the two alpha curves are picking red. So this is an arc on the drawing, but if we glue the two punctures, this is one puncture, and that is another puncture. So this is puncture. Oh, sorry. This is a puncture. And this is another puncture. So if we glue these two punctures, then this arc will glue to a closed curve, which is alpha 2. And if we glue the left and right boundary of this rectangle, we get this curve alpha 1. And so for beta curves, beta 2 is drawn here in green. So this is a curve, that's right. And all the blue things is the curve beta 1. So beta 1 is parametrized by these 4 numbers, P, Q, R, and S. So in particular, its intersection with alpha 1, so it's this x1 up to xp. And Q specifies how many, so the so-called rainbows around each punctures. And R parameterizes how many arcs, so like going from top to bottom. And S is like the shifting. So x1 here is not glued to this x1 minus s. So x1 is glued to x1, but there is like a shift or a rotation horizontally. So this is the 4 parameterization PQRS. And the theorem by Goda. Matsuda, and also Fuji, is that the rank of the Higard-Floer homology of this YK is precisely the number P. So if K means that Y is parametrized by PQRS, well then the dimension of the Higard-Floer homology is precisely P. So it's more details, but there are like P intersections. So this P are the generators of the Higard-Floer chain complex, and there's no differentials. So that's precisely P. And using the algorithm which I just described, we can also compute the upper bound for instanton theory. So so the corollary by me and then is that the dimension of KHI of YK is also precisely bounded by P. Okay. So right. So at last, well, what happens for L space knot? So this is a theorem by by Oswald and Stable. Is that, well, if K inside S3 is a Hegel-Floer L space knot, then what we know is that we can look at the Alexander polynomial of T. So I inside Z will see I times T to the I in the Alexander polynomial. And then, so the rank of the Hegel-Floer homology of the knot is precisely the sum of all the abstract values of those C's. Okay. And in incident theory, well, this there is a theorem by Kronheimer and Morfka that the sum of the abstract values of the coefficients of Alexander polynomial will give us a lower bound for any knot. K inside S3, well, the dimension of the KHI of S3 K is at least the sum of all the abstract values of all the coefficients. So for L space knots, well, this upper bound and lower bound coincide with each other, so we can conclude that the inequality is actually an equality. Okay, so I guess I will stop here. And right, thanks for listening.
Of course, anyone with questions should shout them out.
So Zhenkun, so it's not not just L space knots, but also just any homologically thin knot, like you're only.
Yes. Oh, right. So within one knot, yeah, of course.
Right.
Any homologically thin knot is good. Yeah. We just look at a special class, but yeah, that's true. Yeah, but of course we first need the one condition, because if we're not working with one knot, we don't know if this upper bound is precisely the Runge-Hausdorff Floer homology. Yeah.
I seem to remember a more intrinsic description of a 1-1 knot, which I can't enunciate what it was. Do you know another description that doesn't depend on the Hegard diagram?
Yes, I think so. Yeah, but I'm sorry. So I'm more familiar with the Hegard diagram description because we directly work on that. Yeah. There should be a more intrinsic definition for 1-1 knot.
Oh, does anybody remember what it is? I know Matt.
Yeah, it's the if you think about if you have a two bridge knot, means that you basically have a genus 0 Hegard splitting of the three sphere, and then you have the sort of the arcs going up, 2 arcs going up, and 2 bridges. So 1-1 means it has a 1 bridge presentation with respect to the genus 1 Hegard splitting of S3.
Thank you. That's what I was going to.
But that's essentially, if you think about how you get a knot from the sort of Hegard diagram that Zhenkun drew, that's they're pretty much immediately the same thing.
Yes, yeah. No.
And then the point is that there's this sort of nice standard way, kind of like the way you would write down the I guess the Schubert form for a 2-bridge knot. This is, I guess, is the analog of that for 1-1.
Awesome. Thanks, Danny.
So can I ask, as long as I'm on, Zhenkun, there's no in these theorems where you're getting rank inequalities.
Right.
Is there ever any way that there's actually a map from, you're proving this map from one Floer theory to the other? That's, in effect, you're proving is an injection. Is there any way to organize the argument that way?
So let's see. So let's see. Well, if we keep in the instanton theory, so actually so let me switch to the proposition. So I mean this proposition, right?
Well, you had several propositions that said
right.
that there was an injection.
Right. So yeah. So there is a inequality between the two instanton Floer theories, the instanton Floer homologies, and so are you asking if there is an injection from one to the other?
Yeah.
Let's see. I guess not. Well, it's more like, well, I should say it's more like a spectral sequence other than.
Yeah. Well, that was going to be my second question.
Yeah. So well, yeah. Let's see. Well, what happens? Well, let's say if K inside Y is and what we have is K is 0, well, in the first rational coefficient, modules rational coefficients, then we still have a rank dimension inequality. Let me write it down. So C KHI of YK is at least dimension of I sharp of Y. So what we can do is we can define a differential D1 here, whose square is 0, and then there's a differential D2 defined on the kernel of D1, and then we can inductively define D3, D4, and so on. So this kind of gives us a spectral sequence, and we can show that this finally sort of converges to I sharp.
Mm-hmm. Okay. So yeah, because maybe it seemed that's more natural sort of thing.
Mm-hmm. Yeah.
I have a question. This inequality that's in the middle of the slide right now. On the left and on the right, you can think of those sutured Floer homology as homology of closed manifolds with admissible bundles, right?
Yep.
So, for example, I sharp of Y would be just Floer homology of Y connected sum with the 3 torus.
That's good.
So, if do you know how those closed manifolds relate to each other that show up on the two sides of the inequality?
Let's see. Yeah, it's a good thing. But right. So because, well, what we construct for the instanton Floer homology of the balanced Suture manifold is we look at its closures. Right. So yeah, we construct a closed ring manifold out of the string manifold as boundary. Then so as for what's the relation between the corresponding two closed ring manifold, I guess they are related by a complicated surgery description. So there is a set of surgeries which we can do. So there's like a set of curves inside this ring manifold here, and we can do a set of surgeries and make it things there. But it might not be explicit.
Okay, so you don't know in terms of Corbett moves or something what happens?
Well, I should say I don't study that directly. So, but maybe yeah, we can sort of write out everything explicitly and see if there's a good pattern.
Okay, thank you.
Let me suggest that everybody turn on their camera and we can say hi to each other. We can still ask questions, but just to give us a pretend of being able to see each other.
Yeah, actually, I'm going to say goodbye just because I'm going to do another talk. But thanks, that was a great talk, Zhenkun.
Okay.
Nice to see everybody. Bye.
Yes. So, thank you.
Nice talk.
Thanks.
Are we done saying hi to each other?
Okay.
Yeah, a bunch of taciturn mathematicians here. Oh.
Actually, it's great to see everyone here.
Yeah. Well, one of these days we'll be in person again. Does anybody know the status of this floor theory thing at the Simon Center? I'm going to guess that it's going to be virtual, but it was postponed from last April.
I haven't heard
Oh, yeah. Haven't heard from them since then.
Yeah, I haven't heard anything.
Certainly not good now. Nope. I'll stay on as long as people are on, and then turn it off when they.
I'll help you out by leaving.
All right.
Great luck, Zhenkun. Thank you.
Okay, bye.
Bye, Korea.
So Zhenkun, like 2 bridge knots are 1-1 knots, and they're also alternating. So they're Haggard floor thin. So
right.
you've computed I# for all 2 bridge knots too. Right.
Right, that's good. That's a good question. Actually, I haven't. Well, yeah. Well, I guess that is like, well, what can we do if what we need to do is like we draw Haggard diagrams of surgeries of 2 bridge knots, right? So I'm sorry. So I asking about like the I* of the surgeries of 2 bridge knot or something.
Oh no, sorry. I just meant not I#.
Okay.
KHI.
KHI. Well, but they are alternating, right? So if we're having alternating knots, then that's already been known, right? Because the bound from Hovanov homology is strong.
Oh, okay. I see.
Yeah.
And could you say, wait, so you're saying from Kovanov homology to
yeah, I guess
I#.
Yeah, that should be the story or something. But my intuition is like for alternating knot, we should have already known the Instanton Floer homology. Yeah.
And you're saying why does it follow from the spectral sequence from Kovanov homology?
Well, I'm not sure, but it's my intuition that the Hovanov homologies give us precisely the same rank as the KHI. Is that true? I guess the spectral sequence is just something like collapse.
I know it collapses for enough for like to HF hat of the double branch cover, but I didn't know that we know that also for I#.
I mean, well, you just compute the dimension, right? Sorry, you just compute the rank of the Haggard Floer theory, and you see, well, that's an upper bound for incident theory, but the lower bound coming from Alexander polynomial, and these 2 things coincide with each other.
Okay.
Yeah, that's my intuition. That's my sort of memory for alternating knots. So we didn't stress that alternating knot.
Right. Okay. So the sum of the absolute values of the coefficients of the Jones polynomial of an alternating knot is equal to the sum of the absolute values of the coefficients of the Alexander polynomial.
Yeah, I'm not sure, but I
I mean,
guess
that's what you're saying, right?
No, what I'm saying is like if we look at the reduced Hovanov homology, the rank of the reduced Hovanov homology, and we find it's precisely the same as the sum of all the abstract values of the coefficients of Alexander. Yeah, then this upper bound is from reduced Hovanov homology, lower bound is from Alexander polynomial. It's the same.
Okay.